Okay, hello everyone. My name is Thorben, and I'm going to talk about a topic today that features quite prominently in the book, and is actually quite old, but that I want to somewhat revitalize with this talk. So let's get started. As you can see, the topic is the Hylland-Zeckhauser mechanism. So what is that? So let's get started in the setting of a very classic matching market. And that's a market where you have n agents and you have n indivisible goods that you want to distribute exactly to the agents. So you want to give exactly one good to exactly one agent. For example, let's say houses to these guys. And this market that has one-sided preferences that are linear preferences given by some numbers. So these are cardinal utilities. Every agent has a rational number that signifies how much they like a certain good. And this setting has been around for many, many years. And there's a very well-celebrated paper by Hylland-Zeckhauser from 1979, where they essentially give a very nice mechanism for this allocation problem using what's called a pseudo-market. So the idea is essentially it has 4 steps. Step 1 is that it's always difficult to deal with indivisible goods. So there's a trick. You can make the goods divisible by turning each good into 1 unit of probability shares that you will later run a lottery over. The next step is that you turn the setting into a market. And the way you do that is you give every agent 1 unit of a fake currency. And then now that you have this so-called pseudo market, this market has an equilibrium allocation. So you can take this equilibrium allocation from this market. And lastly, you can use the pretty well-known Birkhoff-von Neumann Theorem, which tells you that if you have an allocation, which in this case is a fractional perfect matching between the agents and the goods, you can run a lottery based on these allocated probability shares. Okay, so let me briefly give kind of the formal setup of this mechanism. Basically, as I mentioned, there are agents and goods, and I will assume that we have an equal number of agents and goods, and we want to assign exactly to each other. And importantly for this talk, I am specifically interested in cardinal utilities, where the agents have numerical preferences over the goods. And then Hylland-Zeckhauser defined an equilibrium concept where basically if you're given an allocation over from goods to agents and prices which are non-negative on the goods, then these are called an HC equilibrium. If every agent gets exactly 1 unit of these probability shares, meaning that the total allocation is a fractional perfect matching from goods to agents. Every agent spends at most their budget, their 1 unit of fake currency. And most importantly, every agent maximizes their utility under these 2 constraints. So they get a bundle of probability shares that maximizes their cardinal utilities under the constraint that they get 1 unit of good and they spend at most their budget. And sometimes there are multiple such bundles, in which case they get a cheapest bundle. Okay, so why is this such a well-celebrated result? The reason is that these equilibria have many very nice properties. So one is that they are envy-free, or to be a little bit more exact, ex-ante envy-free. So this lottery, no agent would want to exchange their own bundle of these shares with another agent. They are Pareto optimal, meaning that there's no way to improve one agent without hurting another agent. And they also satisfy a weak notion of strategy proofness, that if the market is in some sense large enough, then agents cannot benefit by misreporting their cardinal utilities. Okay, and based on this, you might say that this particular setting of a matching market is kind of a solved problem. In particular, Hylland-Zeckhauser, they actually showed that these equilibria always exist. And moreover, the only kind of flaw of this is that, okay, it's not perfectly strategy proof, but actually it's known that you cannot get envy-freeness, Pareto optimality, and strategy proofness at the same time. So you might consider this kind of a best possible result. And there's kind of this general belief that once you've set up a pseudo market, now you have a very natural mechanism. You can give agents their fake currency, and then they can trade amongst themselves and find this equilibrium somehow, and there's your mechanism. But I want to argue that in this talk, that actually there is still a lot of really interesting research in cardinal matching markets like this, because this problem is not quite solved. And the reason is that there are two major deficiencies that this pricing-based approach has for matching markets. The first is already in the title of the talk, and I will get into this in more detail. And that's the fact that these equilibria are near impossible to compute. So both in theory and in practice, as we will see. And the second is that when you think about this matching markets that I just described with the HC equilibrium, it's a very restricted setting. It's linear utilities, one-sided. And if you compare that to all the beautiful models we have in general equilibrium theory that are pricing based, there's a pretty big paucity of models for matching markets. Okay, so let's get started on the intractability. So in terms of computing these equilibria, there are essentially kind of only three main results. The first is the original proof, which shows that the equilibrium exists. And it uses Kakutani's fixed point theorem, and it's highly non-constructive. And they say as a remark that if you want to compute the allocation, well, you can do like a grid search over the prices, which is extremely inefficient. Then there is an algorithm that uses a technique called algebraic cell decomposition. And this algorithm, it's interesting maybe theoretically, but in practice, even for, say, 5 agents and 5 goods, you need somewhere like 10 to the 80 steps if you run this algorithm, which is more than there are atoms in the universe. And in terms of polynomial time algorithms, there is one algorithm, but it only works for bivalued utilities, where every agent only has 2 types of utilities, a highly restrictive setting. So why has there been so little progress on this computation? So this was a question that was asked recently in a paper by Vazirani and Yannikakis, and they started giving some answers. So the first thing is that these equilibria can be irrational. So there is an instance, small instance like this, where there is a unique HC equilibrium, which is irrational. And from a complexity theory point of view, they showed that finding these HC equilibria is in a complexity class called fixed P, and finding approximate equilibria is in a complexity class called PPAD. Now, for those of you that don't know what this means, so basically these classes, fixed P and PPAD, you can think of them as kind of analogs of the class NP that you all know, which is highly believed to be intractable, except that in this setting, we always know an equilibrium exists, so we are given the assumption that one exists, and we want to find it. Both of these classes represent problems of this type, with one major distinction being that we already know HC equilibria are irrational, and so they cannot actually be in this class PPAD, which only allows rational solutions. But this kind of so they show that finding these equilibria is in this class, but perhaps the more exciting problem is whether it is complete or hard for these classes. And one of these questions was resolved very recently, where these long list of authors here, they studied this problem, and they showed that finding an epsilon approximate HC equilibrium is in fact PPAD hard for inverse polynomial epsilons. And kind of to bring this home, what does this mean? So being PPAD hard means that it's kind of in the same league as many other famous problems in computational economics, such as finding like general Nash equilibria, finding market equilibria in certain markets. And in fact, it's even computational equivalent to Kakutani's fixed point theorem and Brouwer's fixed point theorem. Okay, so that was a lot of bad news. But I think in research, bad news is always good news, because if something is impossible, then it opens a new direction for interesting research. And I think in this case, the path forward is that I think we need to go back on cardinal matching markets and look at the properties that we want to have. So there's kind of 4 properties that we want from mechanisms in general. We want things to be fair, ideally envy-free in this setting. We want efficiency, ideally Pareto optimality. We want strategy proofness, ideally DSIC. And as a computer scientist, I want this. I want polynomial time. I want a mechanism that you can actually implement. And this raises, so, as I said already, by the way, like just these 3 together are impossible. So you can kind of look at every single combination of all these properties, and various results are known. But what I think is one of the most fundamental problems is the question of just what about just fairness and efficiency. So the HZ solution tells us that there are solutions which are envy-free and Pareto optimal, but we don't know of any way to compute such solutions. So there's a major open problem in cardinal matching markets, which is to give a polynomial time algorithm which finds Pareto optimal and envy-free allocations in this very simple linear one-sided matching market setting. Or indeed, to show that this is hard. Both of these are quite interesting. And in wake of this major open problem, I want to pose the question of what is actually the best possible that we know right now. So if you try to fix, say, Pareto optimality and polynomial time, what is the best fairness guarantees that you can actually achieve? And that brings me into my next major topic, which is an alternative approach to cardinal matching markets, which is called Nash bargaining. Okay, so Nash bargaining is a very old idea. And the idea of Nash bargaining is that, let's say you have 2 agents who, let's say, own some nice vacation homes. So one agent has a vacation home on the beach, and the other agent has a vacation home in the mountains. And they both like their vacation homes, but they don't want to spend every single vacation there. So these 2 agents can meet, and they can say, look, I have this utility right now, you have that utility, and maybe we can bargain, we can exchange some time in our houses and improve our situation together. So formally, basically, these 2 agents, for every possible way that they can kind of trade their time in their houses, it forms a set of possible allocations, and each of these allocations has utilities for both agents, which forms this utility space. And there's some initial point called the disagreement point, which is where the 2 agents started. And Nash asked the question of, where will these 2 agents end up with in some idealized bargaining scenario? So these are disagreement utilities. And he started wondering about kind of what axioms we might make for this bargaining scenario. And he came up with 4 axioms. The first 2 are Pareto optimality and symmetry. Symmetry meaning equal agents should be treated equally in this bargaining process. And the last 2 I won't go into too much detail: invariance under affine transformations and independence of irrelevant alternatives. But the kind of main thing I want to point out is that under these axioms that Nash introduced, he showed that assuming the space of utilities is convex, then there is actually a unique point called the Nash bargaining point somewhere above these 2 disagreement lines, which is the ideal outcome of this bargaining situation. So the theorem that he showed is that if this set of utility vectors is convex, then there is a unique point satisfying these 4 axioms. And this point is the maximizer of the product of the utilities minus the disagreement utilities. This you might also know as the Nash social welfare. Now, why is this interesting to me as a computer scientist? Well, the reason is that this is inherently a polynomial time thing, because you're maximizing a log concave objective over a convex set. Meaning that if you take the log of this, you're maximizing a convex function over a convex set, and that's a convex program. And there are many practical and theoretical results to solving convex programs. Now, Nash bargaining and these kind of pricing-based mechanisms actually have a long history. I don't want to go into all the details, but I do want to point out two results. The first is the Eisenberg-Gale program. So probably many of you know this, that if you have a linear Fisher market, which is kind of the analog of this market that I just described, except there's no matching constraints, so you can assign multiple goods to one person, then it actually turns out that Nash bargaining in this setting is equivalent to a linear Fisher market, and they're both modeled by this so-called Eisenberg-Gale program. But as soon as you move into other settings, such as, for example, linear Arrow-Debreu markets, it turns out that Nash bargaining and pricing mechanisms in general diverge. They do not give the same results, though Nash bargaining often turns out to be a rational convex program and have rational solutions. And in fact, in some settings, there are very nice combinatorial and strongly polynomial time algorithms, which is why I'm in particular interested in applying these techniques to matching markets where we have no nice algorithms. Okay, so there's a recent work which studied Nash bargaining as a tractable and real-world alternative to Hylland-Zeckhauser. This paper, they give various practical algorithms based on convex programming techniques such as Frank-Wolf and cutting planes. And they show that you can easily solve matching markets up to, say, 20,000 agents in an hour, which, again, if you compare that to the HZ solution, where even for n equals to 5, I will not be able to guarantee you any solution ever. So there's a rather big gulf in terms of what you can do experimentally. And also, as I will talk about a bit later, there are many other models of matching markets that you can extend these techniques to. So the nice thing about Nash bargaining, as I said already, is that it's a convex program. But in particular, it's not just any convex program. It has a very particular form where you're maximizing the sum of the log utilities over the space of feasible allocations, which in our case is matchings. And the matching polytope is not just any polytope, it has a lot of nice structure. And using this structure, we showed that you can actually give some very nice simple algorithms. There's, in fact, like a multiplicative weights-based procedure that you can use to solve this problem. And there's also a conditional gradient type algorithm, which uses a matching solver as a subroutine. And using these algorithms, you can get much more reasonable runtime bounds compared to exponential time. You can do things in like n log n over epsilon squared. Okay, so now I want to kind of come back down to reality. So what's the reason that Nash bargaining is not the ultimate solution? Well, the reason is that Nash bargaining is neither envy-free nor strategy-proof. So there are some very small examples like this one. And in fact, there are even some examples that use only 0-1 utilities where Nash bargaining does not give you an envy-free solution. But I don't want to say that Nash bargaining is not fair at all. It does have some fairness properties. So one is obviously one of the axioms. It's symmetric. It treats equal agents equally, which is kind of nice, but very easy to achieve. But it also has two other properties. One is that it's proportionally fair, which means that if you try to increase one agent's utility by, say, a factor of 2, then you cannot do that without harming the other agents by a factor of 1/2. And also, Nash bargaining satisfies a relaxed form of proportionality or equal share fairness, meaning that every agent gets at least half of what they would get if you just assign the items totally at random. Okay. Now, there is one last thing I want to point out. So Nash bargaining, as I said, is very well understood from a computational perspective. But there is one, I think, very interesting question which is still open. And that's the question of dynamics. So Nash bargaining in general there are certain dynamics that converge to a Nash bargaining solution where the two agents bargain with each other. But those dynamics turn out to be very unnatural in this case of matching markets. So I pose as an open question to find natural decentralized dynamics where the agents interact in such a way that it converges to this Nash bargaining solution. Okay. Now, the last topic I want to talk a little bit about is going beyond the simple one-sided linear matching market setting. So as I mentioned, Hylland-Zeckhauser is in some ways analogous to the linear Fisher market, which is the most elementary model that we have in general equilibrium theory. If you want to go beyond this, for example, to things like a linear Arrow-Debreu market, where the agents already bring some endowment of goods into the market and then trade amongst each other, or if you want to go into markets that have non-linear utilities, what can you do? The other thing I want to point out is there are certain markets that are specific to matching markets, such as two-sided markets like kidney exchange, or non-bipartite markets like roommates markets, where the same question can be raised. What can you do in terms of extensions of Hylland-Zeckhauser? Okay, so let's answer that question. For the exchange market, actually Hylland-Zeckhauser already mentioned in their original paper that while there is a very natural extension of their equilibrium to an endowment setting where agents are trading, equilibria in general fail to exist. And given this, there are some ways around this. So there's a model called alpha slack equilibria, where you construct a hybrid model between a trading economy and an HD model. So basically, you give everybody just a tiny epsilon of fake currency, and the rest happens through exchange. And in that setting, equilibria do exist. And there's even a result where we show that there's a slightly relaxed notion of this called epsilon approximate equilibrium, where you can give algorithms for bivalued utilities, which is, as I mentioned earlier, also the only case where we have algorithms for HC. Okay, and there's one more result I want to mention, which is that you might say, okay, but even for Arrow-Debreu, equilibria do not always exist. There are certain conditions that you need. For example, a well-known sufficiency condition is that you have what's called a strongly connected demand graph, and maybe under this condition you have an ADHD equilibrium, but in fact, that's not the case. So there are many examples where these ADHD equilibria do not exist, even with 0-1 utilities and further restrictions. But of course, Nash bargaining does still exist. In fact, you have to probably look at this twice to even see the difference between this and the non-exchange version. The difference is that we include this disagreement point. Okay. Next, I want to mention two-sided markets. So for two-sided markets, the question was not actually raised in the paper. So the original HC paper, as I mentioned, it already says, well, what about extensions to endowments? Okay, we can't do it. But they didn't actually consider these different markets that are specific to matchings, really, of two-sided markets, where you have agents on both sides or agents in a non-bipartite setting. And here, I mean, this question is a little bit general. I mean, what exactly is a pricing-based mechanism? However, one thing I can tell you is that in two-sided markets, there are, in general, no envy-free and Pareto optimal solutions. So if you have a setting like this is with symmetric 0, 1, 2 utilities. So this edge means that both of these agents have utility 2 for this pair. These agents have utility 1 for this pair, and the rest is the edges which are not here represent utility 0. Then in this setting, there is no fractional perfect matching, which is both envy-free and Pareto optimal. And the same goes if you go to asymmetric 0, 1 utilities. So here, this means like this agent has utility 1 for this agent, but this agent has utility 0 for this agent. So same thing there. There's no envy-free and Pareto optimal solutions. So if you're looking for a pricing-based mechanism that has kind of the same properties as HC, where the prices are independent of the agents and non-negative and so on, then they would imply these properties, and so you cannot find it. Okay, let me talk briefly about envy-free and Pareto optimal allocations in general. So these examples that I just showed you, you might notice that it's actually a little bit hard to verify that they are examples because there are, of course, infinitely many allocations, which could be envy-free and Pareto optimal. But as a kind of general meta result, you might say, for any matching market like this with linear utilities, you can see that there is a kind of a trick, which is that the envy-free solutions in general form a polytope. So this is, for example, in the case of a one-sided market where you have agents and goods, then the set of all envy-free solutions is given by the matching constraints and additional constraints that say that no agent envies another agent. And what this means is that if you look at the space of all utilities that can be achieved by allocations, the set of envy-free utilities is a polytope inside of the space. And a solution is envy-free and Pareto optimal if it lies on this frontier, and it's also on the boundary of this envy-free polytope. And then probably already from this picture, you can see that using some standard polyhedral theory, you can show that envy-free, there's always an envy-free. So if there is an envy-free Pareto optimal solution, then there's always envy-free Pareto optimal solutions, which are vertices of this polytope. And that means that you can find these solutions in practice, typically in the following way, which is that you can just find some random vertices of this polytope, for example, by optimizing in certain directions. So you might optimize in a direction, use an LP solver to find a vertex, check if it's Pareto optimal, which is another linear program. And you can repeat this until you might find, if you're lucky, an envy-free Pareto optimal solution. As I said, for the one-sided linear market, such solutions always exist because of HC. In other markets, they often do not exist. And that's basically, how I constructed these examples. Okay, so I have a couple more minutes. So let me mention some more positive results also. So in the case of these two-sided matching markets, again, not a big surprise is that Nash bargaining extends easily. In fact, here, the only difference is that you sum over agents on both sides. The algorithms to solving this program efficiently are affected a little bit, so it's not quite as easy as it seems, but it's still possible to solve this very efficiently, both in practice and in theory, even if you add some endowments as well. And in the case of 0-1 utilities, you actually get a little bit more. So notice that when I introduced the counterexamples, I showed you an example for symmetric 0-1-2 utilities and asymmetric 0-1 utilities. And there's a reason for these two examples. It's because if you actually go to symmetric 0-1 utilities, somewhat surprisingly, there are actually these pseudo-market equilibria where the agents have equal fake income. This is an old result by Bourbonnais and Moulin, but technically they don't show that it's polynomial time. But if you're familiar with this 0-1 HZ algorithm by Vazirani and Yannakakis, then it's fairly easy to show that you can also do this in polynomial time. And in fact, these equilibria also exist in the case of non-bipartite graphs. So even if you remove the bipartiteness condition, the 0-1 case goes all the way to the end. You can do it in polynomial time on general graphs. And as soon as you add 3 utilities or asymmetry, it all breaks down. And yeah, Nash bargaining, same story. In a non-bipartite graph, as I'm sure many of you know, the matching polytope gets a little bit complicated. You have exponentially many constraints, but there are various techniques to get around this too. Okay. And last thing is I want to just very briefly touch on nonlinear utilities. So nonlinear utilities are a bit interesting in this case of matching markets. So if you start from the original setting that Hylland and Zeckhauser studied, where you have indivisible goods and you essentially do this trick of creating probability shares, you very naturally end up with linear utilities because the agents care about the expected utility that they get from the lottery. However, there are settings like this, say, house sharing problem that I told you about earlier in Nash bargaining, where there are the agents have preferences that are not quite linear. For example, I might want a certain mix of the beach and the mountain home more than just having the beach home or the mountain home, because I like variety. So that's a case of a nonlinear utility. And it turns out that under certain conditions on the linear or on these utility functions, equilibria do exist, though of course this is highly non-tractable. So it uses very similar techniques with Kakutani's fixed point theorem. We have no idea how to compute these equilibria, and also it doesn't quite cover all utilities that you're interested in. Whereas with Nash bargaining, again, you can do pretty much anything. So you can compute even just non-separable piecewise linear utilities, such as Leontief utilities. You can compute up to thousands of agents quite easily. And we actually show that for separable piecewise linear functions, the utility functions, concave, of course, separable piecewise linear concave utility functions, you can find solutions in polynomial time as well. And lastly, I have one more open question, which is that I now introduce to you all these various models that you cannot solve with HZ, where we either know pretty well that you cannot solve them, or we just know that they're very likely to be computationally intractable. And so I want to kind of revitalize this research in cardinal matching markets and ask the question of what are the trade-offs that we can achieve in terms of efficiency and fairness, for example, for two-sided matching markets, or for nonlinear utilities, etc. And of course, what of that is achievable in polynomial time? So I leave you with that question, and I hope you're all now more interested in cardinal matching markets than you were before. And yeah, that's it.
Thank you, Thorben. I guess we have time for questions. So before, I just want to make a comment about lunch. So like Sandy said, you're on your own for lunch. If you want, you can go next door to the business school. That's the closest distance. There's a cafeteria there. But if you walk south, there's some Bancroft. There are several restaurants. If you're very hungry, there's a very good Chinese restaurant with enormous servings. Otherwise, if you continue walking down towards Telegraph, there are sandwich places, stuff like that. So those are
Yeah, so one of the important things about Hylland-Zeckhauser was that after they allocated probabilities, there existed a way to implement that.
Yes.
Didn't say anything about that.
Right. So because you can typically use the same technique. So the way that they implemented it, yes. So you can use that even for non-bipartite markets, and that is polynomial time. So there is a polynomial time way to do this implementation. There's also lots of interesting questions about the actual integral allocations that come out of this, like whether the integral allocations have some fairness properties as well. A lot of interesting research there, but yeah, I didn't go into that. Yeah.
I misunderstood your
Yeah.
Hylland-Zeckhauser model. You said that finding envy-free and Pareto optimal is difficult.
So so the Hylland-Zeckhauser achieves those properties, but it's difficult to compute. So we know that it's hard to compute the equilibrium.
Not equilibrium, just two properties.
Yes, so just finding those two is hard. Yeah, well, we don't know if it's hard. That's another thing.
But we can just write out linear program.
No, so it's because the Pareto optimality is not.
You can just take, because the envy-free is a code, the thing an act is envy-free is envy for the thing that in that range will need to be envy-free. And you take an objective, say maximum welfare, it's going to achieve envy-free.
So you can optimize over, let's say, the envy-free and pick a direction and go as far as, but that gives you a solution which is optimal among, like Pareto optimal among the envy-free solutions. But there are envy-free solutions, there are many examples where you pick a direction and it gives you an envy-free solution that is optimal among all envy-free solutions. But there are solutions which are not envy-free, but which are better for everyone. So that's yeah. So that's kind of the hard part, is that it's easy to find solutions which are optimal among envy-free just by running linear programming. But finding solutions which are Pareto optimal overall and envy-free. That's hard. Yeah.
So one problem with Nash bargaining is that it's not monotonic with respect to the disagreement points.
Yeah, so Nash bargaining has multiple issues. So it's very there's also, in terms of another thing I didn't really talk about too much, is in terms of the strategy proofness. Like, you have a lot of benefits in misrepresenting your disagreement points. So there are definitely various issues. That's why I think, but this is, as far as I know, the best we know in terms of fairness properties for meshing markets, which leaves like a pretty big gap that I'm very interested in. Okay, I think we're well on time. So, and I guess I'm ending the session. And feel free to go to lunch. And when is it? When do we restart? 1:30. 1:30? Okay, then see you at 1:30.